So here we go, an early start. So Cold War 1956 was in fact the first nuclear reactor to generate electricity for the grid. It wasn't the first nuclear reactor to operate, of course, but it was the first one to provide energy to the grid in any significant amount. The United States and Russia had also got reactors working at that point. And these are called Magnox reactors. And in fact, we sold a Magnox reactor to Japan. We sold a Magnox reactor to Italy, which are also in the processes of decommissioning. These, from an engineering point of view, they were, over-engineered is an overused term, but put it like this. There's no doubt that these reactors could have kept going for another 100 years, except that it wasn't economic. And part of the problem for that is these are the fuel canisters that were used in those sets of different Magnox reactors. So the engineers in the audience will have spotted a fatal flaw, and that is that they were all different. So all the reactors were bespoke, and all the fuel was bespoke. And if you want to recycle the fuel, of course, what you want is something that's nice and even across the different reactor designs. Unfortunately, we didn't learn that. We were very keen on tinkering, as you can imagine, very British thing to do. And so from an economic point of view, that wasn't optimum, definitely suboptimal. These are the existing nuclear reactors that we have at the moment. On typically provides around 17% of the UK's nuclear energy. On a very good day, it can be up to sort of like 22 or even 24. On a bad day, it's down to sort of 14%. You understand, of course, as well as I do, about balancing across different generating capacitors. And one of the flaws in nuclear reactors is that you have to take them offline to refuel. Except, not necessarily with these designs, and these are the advanced gas-cooled reactors. That's the date the reactor design was started, and that's the date that it came into operation. It went into operation, came off and went back on again. Now, what do you spot again, which is the typical British sort of issue? They're all different. Yes, there's a lack of consistency. The fuel, however, was consistent. So our reprocessing, remember the UK has done a tremendous amount of reprocessing, our reprocessing was aided through that. But again, this was a bespoke UK design. We didn't sell them to any other country. They're much higher temperature reactors than that of our single PWR reactor, that's Sizewell B. By the way, each of these have, you can almost sort of see it, they actually have two reactor cores. So it's a single station with two cores. Whereas Sizewell B here, there's a single station with a single core. So we're using carbon dioxide as the way to remove the heat. It's the coolant. So really different design than the rest of the world, really. The idea, higher temperatures, greater efficiency. That's true, but if you are the only country producing that design, what it means is, of course, you don't have that whole international community to aid you in the development of your reactor type. So this is the situation. Those are the early Magnox reactors. The late Magnox reactors, in fact, Wilva is still operating. It's a Generation 1 reactor. It's the last, I think, Generation 1 reactor generating generating electricity anywhere in the world. It could go on for an awful lot longer, but we don't manufacture fuel anymore. The fuel manufacturer stopped producing fuel about 8 years ago now. Or was it 10 years perhaps by now? If it was, that reactor could in fact go for much longer. These are the Agr stations, our single PWR, and PWRs is what we will move forward with, or certainly light water reactors. We will be looking at, in fact, PWRs and BWRs. I'll come on to that in a minute. So here's the legacy that I mentioned right at the beginning. That's our fast reactor program. That's an iconic dome, a sphere structure, which I believe is now, we can't actually get rid of the sphere itself. I think there's a preservation order, there's an actual preservation order on that. Oh, I mean, there are some wonderful stories. I mean, so for example, here at Hunterston A, is a Magnox reactor that went out of operation, and the local fishermen complained because they used the lights at Hunterston A to guide them back into the harbour. You heard this story. So they've had to put the lights back on inside Hunterston A. And of course, these same fishermen were perhaps less keen on nuclear at other parts of the time. There are lots of stories like that. This is Sellafield, where we did a lot of the reprocessing. And if you look very carefully at some of these photographs, you can see, actually nearly all of it's been removed now, but you could see the spent Magnox fuel pins in the bottom of that. Anybody spot anything interesting about this photograph?
It's open air.
It's open air, absolutely. And there are a variety of stories about seagulls dropping various little crustaceans into the pond and then swimming around in the pond water, and with some interesting genetics associated with that. Allegedly, of course, actually it turns out that's not true at all, but still. And eventually they dealt with the little crustaceans by adding pond decontamination to that. Anyway, fortunately, one pond opened, the rest of them closed, and we're dealing with that legacy at the moment. But it goes back to this thing about being an early entrant. Of course, as an early entrant, you make mistakes. And as an early entrant, you can see we have Magnox stations, we have reprocessing, we have a fast reactor program, we have all sorts of research sites. I think that's Harvard, where I did my PhD at Theoretical Physics Division. We have a variety of different things to look at, which makes us, of course, a very interesting partner for any decommissioning activities. Because if there's a challenge, we've had a look at it. So it is, in fact, a double-edged sword. In terms of the amount of waste that we have, and what else are you going to do to describe large amounts of waste, then of course use the unit of the St Paul's Cathedral. It's a useful volume that we can understand. It's Olympic swimming pools and St Paul's Cathedrals, the non-SI unit. So light water, LLW, low level waste, intermediate level waste, and high level waste, and a variety of spent fuels and so forth. That is, of course, the sort of total volume. But one of the things, due to the fact that we engaged in so much reprocessing, is we have an awful lot of civil plutonium. Indeed, we have the world's largest stockpile of civil plutonium. Civil plutonium is different from other types of plutonium in that it has a number of different elements, americium in particular, that make it unuseful for other than putting into mixed oxide fuels. We are deciding at the moment, or coming to decisions as to how we will utilise or dispose of our civil plutonium stockpile. But again, we are having to do the research, we are having to think about these sorts of problems, which I believe makes us a very interesting partner. This is, so anyway, we've got about, in total for everything, we've got about a St Paul's Cathedral. By the way, in terms of high-level waste, the really radioactive stuff, which has like 98% of the radiological burden, you could get it all into about 3 rooms this size. The ceilings are a bit high. Double the ceiling, make 3 of these, so 6 times the volume of this room. We could contain all the high-level waste we've ever produced. Most of it's in the form of vitreous, so it's in glass, it's immobilised in glass and steel containers. And that's in 50 years of reactor operation. The rest of it is intermediate and vast amount of low level.